Hello everyone, I am Dr. Venkateswararao, Assistant Professor, PG Department of Chemistry, Sri Vayan College, Narsapur. Today I am here with a new concept, that is acids and bases. Why acids and bases? Why? Because I can integrate the earlier concepts with this concept, right? As you are all familiar with acids and bases, I shall make an attempt to explain this concept in nutshell. The word acid derived from Latin word acidus, which means sour, which is attributed to their sour in taste, and the word base is derived from Latin word alkali, which means ashes of plant, which is attributed to the fact that we felt soapy when we touch them. To explain this concept, I shall take a group of acids and bases by which I can explain the concept of acids and bases. Here are the group of acids and bases: HCl, acetic acid, CO2, SO2, AlCl3, BF3, and NaOH, NH4OH, NH3, PH3, Na2CO3. These are the group of acids and bases. There are subtle definitions for acids and bases according to different theories. We shall learn those theories one by one. The most primitive theory is that Arrhenius theory, Arrhenius concept. Arrhenius concept of acids and bases, or Arrhenius theory. Arrhenius acid is a chemical compound or a chemical substance which furnishes or which produces H plus ions in aqueous solution. For example, HCl can furnish H plus ions and one more example is CH3 COOH, that is acetic acid, which can furnish H plus ions and acetate ion. I shall explain why I wrote double-headed arrow. There is a significance for this double-headed arrow in case of acetic acid. I shall explain this concept in the later classes, in the upcoming classes. So, Arrhenius acid is a compound or a chemical substance which furnishes H plus ions in aqueous solution. Examples are HCl, which can furnish H plus ions, acetic acid, which can furnish H plus ions. and Arrhenius base is a chemical compound or a chemical substance which furnishes OH minus ions in aqueous solution. For example, sodium hydroxide, NaOH, which can furnish OH minus ions and Na plus ions. NH4OH, ammonium hydroxide, which can furnish NH4 plus ions and OH minus ions. And the strength of the acid or base depends upon its tendency to furnish proton or tendency to furnish H plus ions or OH minus ions in the aqueous solution. That means HCl has a greater tendency to furnish H plus ions. That's why Arrhenius regarded HCl as strong acid. And acetic acid has a less tendency to furnish H plus ions. Therefore, Arrhenius regarded acetic acid as weak acid. And coming to the base, sodium hydroxide has a greater tendency to furnish OH minus ions. So, it is regarded as a strong base. And NH4OH, ammonium hydroxide, it has a less tendency to furnish OH minus ions. Therefore, Arrhenius regarded that NH4OH is a weak base. Okay, and Arrhenius extended his theory. Acids, the reaction between acids and bases, or usually the reaction between acid and base is called as neutralization reaction. That is, the reaction between acids and bases or neutralization reactions are the reactions between H plus ions and OH minus ions. And Arrhenius stated that water is amphoteric substance because it furnishes H plus ions and OH minus ions. So, water is amphoteric substance which furnishes H plus ions and OH minus ions. And moreover, Arrhenius said that neutralization reaction is the reaction between H plus and OH minus ion. So, based on this theory, we can pick up the Arrhenius acid from this group of acids. From this Arrhenius concept, we pick up HCl is a Arrhenius acid because it can furnish H plus ions in aqueous solution, right? And acetic acid, it can also furnish H plus ions in aqueous solution, but it has a less tendency to furnish H plus ions. And we can pick up Arrhenius base from this group of bases. That is, we can said that sodium hydroxide is a Arrhenius base because it can furnish OH minus ions, and NH4OH, it can furnish OH minus ions. And of course, NH4OH is a weak base because it has a less tendency to furnish OH minus ions. So, according to Arrhenius concept, we can pick up the Arrhenius acids from this group of acids and from this group of bases. But what happens in the case of AlCl3 and BF3? How they are regarded as acids? I wrote that AlCl3 and BF3 in the group of acids. How can we regard that AlCl3 and BF3 as acids, or CO2 and SO2 as regarded as acids? That means Arrhenius theory fails to explain the acidic nature of salts like AlCl3 and BF3. Moreover, Arrhenius stated that acid base or neutralization reaction is the reaction between H plus and OH minus ion. But when we consist with the reaction, for example, if you take CaO plus CO2, that gives rise CaCO3. CaCO3. It is also a neutralization reaction. Okay, it is a base and it is a acid. And let us take another example. HCl plus, let us take another example. I shall explain this concept with this example. So, according to Arrhenius, acid base or neutralization reaction is the reaction between H plus and OH minus ions. But when we look at this reaction, it is a base and it is a acid. This is acid base reaction, but in this reaction there is no involvement of H plus ions or OH minus ions. So this Arrhenius theory also fails to explain the neutralization reactions, particularly in this particular reaction, right? And when we go for NH3 plus HCl gives rise to NH4Cl. It is a base and it is a acid. Here only involvement of H plus ions are there, but there is no OH minus ions. It is also a acid base reaction, but this reaction does not involve, and this reaction OH minus ion is not included in this reaction. But according to Arrhenius, acid base or neutralization reaction is the only reaction between H plus and OH minus ions. Therefore, Arrhenius theory, it fails to explain the acidic nature of salts like AlCl3 and BF3, and basic nature of CaO, NH3. Those actually when we consult with AlCl3 and BF3, these do not have H plus ions, but they act as acids, and CaO it do not have it could not have OH minus ions, but it acts as a base. NH3 it could not have OH minus ions, but it acts as base. So Arrhenius theory fails to explain these reactions or these compounds. Why? How that compounds acts as acids or bases. And moreover, it fails to explain the acidic nature of SO2, CO2, NH3 and CaO. Okay, so Arrhenius theory fails to explain those acidic nature, but this limitation has been overcome in the presence of water as solvent. Let me write the reactions of those compounds. For example, if you take CO2 plus water gives rise to H2CO3, and SO2 plus water gives rise to H2SO3, and SO3 plus H2O gives rise to H2SO4, and NH3 plus H2O gives rise to NH4OH. Right, and CaO plus H2O plus H2O gives rise to CaOH twice. Okay, so actually according to Arrhenius, CO2 is actually CO2 is an acid and SO2 is an acid. AlCl3 is an acid, BF3 is an acid, but Arrhenius theory, the theory could not provide how those compounds act as acids, but that limitation can be overcome by when these compounds dissolved when in the presence of water as a solvent, it can furnish H2CO3. When we dissolve CO2 in H2O, it forms H2CO3, and H2CO3 can furnish H plus ions. When we dissolve SO2 in water, that forms H2SO3, it can furnish H plus ions. And SO3, when we dissolve SO3 in water, that forms H2SO4, and it can furnish H plus ions. NH3, when we dissolve it in water, it can furnish OH minus ions. Similarly, it can also furnish OH minus ions. And these compounds can furnish H plus ions or OH minus ions. All these compounds can furnish H plus ions or OH minus ions only in the presence of water as a solvent. What happens if we remove this water as a solvent and instead of that water, if we take another solvent, are these compounds are able to furnish H plus ions or OH minus ions? No. No. Answer is certainly no. These compounds can furnish H plus ions or OH minus ions only in the presence of water as a solvent. But if you take another solvent, those compounds could not produce H plus ions or OH minus ions. Okay, so that's why these compounds are called as non-aqueous acids. These are called as non-aqueous, and in the upcoming classes we can say that these compounds CO2, SO2, SO3, these are called as non-aqueous acids. Okay, and NH3 is a non-aqueous bases. We can say that these are non-aqueous acids and it is non-aqueous bases. If we use another solvent instead of water, right? This is about Arrhenius theory. Okay, so Arrhenius theory fails to explain the acidic nature of some salts like AlCl3 and BCl3, and non-aqueous acids like SO2 and HO2, CO2, SO2, SO3, CO2, but that limitation can be overcome in the presence of water as solvent, So, Arrhenius theory fails to explain the acidic nature of AlCl3, BF3, and basic nature of ammonia, NH3, CaO. It fails in the case of these compounds, and it fails in the case of these compounds. Next, after this limitations, Bronstead-Lowry theory of acids and bases came forward to explain the limitations or to explain the acid-base concept. Bronstead-Lowry concept. And usually we call it as a Bronstead theory, and Bronstead acid is proton donor and Bronstead base is proton acceptor. And water, this theory also stated that water is amphoteric because it can donate proton, it can accept proton, and the proton donated by an acid does not exist alone and it always solvated. Do you catch this point? Proton donated by acid cannot exist alone, always it solvated. That is, for example, acetic acid in water can donate H plus ion, CH3, COO minus and H plus ion, and that H plus ion cannot exist alone. It forms H3O plus ion. That means it always solvated. It is always solvated. And moreover, a cation, according to Bronstead-Lowry theory, a cation acts as acid. For example, if you take Na plus and dissolve water, it gives a cation acts as an acid, NaOH plus OH, Na plus, for example, NaOH and H plus ions. H plus ions. And a base can act as an anion can act as acid. Sorry, an anion can act as a base because that can liberate that can donate OH minus ions. Okay, so a cation which can donate H plus ions, therefore a cation can act as Bronstead acid. An anion can donate OH minus ions, therefore we can say that an anion, Bronstead said that an anion can act as a base. And acid base pair differ by H plus ion is known as Bronstead conjugate acid base pair. I repeat, acid base, a pair of acid base differ by H plus ion known as conjugate acid base pair. For example, acid. According to Bronstead, proton donor is an acid, that is, acid can donate H plus ions. For example, if you take HCl, it can donate H plus ions and it forms Cl minus ion. So HCl is an acid and Cl minus is known as a conjugate, its conjugate base, right? For example, C2H2, if it lost H plus ion, it forms C2H minus ion. It is acid, Bronstead acid, and its conjugate base is C2H minus. And C2H5OH, its conjugate base is C2H5O minus. Okay, and if you take Bronstead base and this is acid and it is conjugate base, these two are differ by H plus ion, these two are differ by H plus ion, these two are differ by H plus ion. So this can called as a conjugate acid base pair. For example, if you take a base, we can get a conjugate acid. Base accepts a proton. For example, NH3, if you take base NH3, it accepts a proton, that forms NH4 plus. And if you take C6H5NH2 paired in, okay, it accepts a proton, that is C6H5NH3 plus. These two are differ by H plus ion. So it is conjugate acid base pair. Okay, of course, this theory can explain the conjugate acid pair and which cation. This theory states that cation acts as an acid and anion acts as a base, but it fails to explain the acidic nature of CO2, SO2 and AlCl3 and BF3, and it fails to explain the acidic nature of remaining certain bases. So this theory also fails to explain the limitations of Arrhenius theory. Okay, so Bronstead-Lowry theory or Bronstead theory also fails to explain the limitations of Arrhenius theory. So another theory, that is Lewis theory of acid bases, has came forward to explain the acid base concept. So Lewis concept. Or Lewis theory. Lewis acid is electron pair acceptor. Lewis acid is electron pair acceptor, and Lewis base is electron pair donor. Right? Lewis acid is electron pair acceptor and Lewis base is electron pair donor. And examples for Lewis acids are Lewis acids, compounds in which central atom has incomplete octet can act as Lewis acids. For example, BF3, AlCl3, BBr3, Ga gallium chloride, GaCl3. These are the compounds in which the central atom, here boron, here is aluminum, here is boron, here is gallium, has incomplete octet. So compounds in which central atom has incomplete octet can act as Lewis acid, and compounds in which central atom has vacant orbitals can act as Lewis acid. For example, SnCl2, SnCl4, PF4, SF4. These are the examples for compounds in which central atom has vacant orbitals. Those are Lewis acids. And third Lewis type of acids are compounds with multiple covalent bonds, that is CO2, SO2, CS2. These compounds with multiple covalent bonds, these compounds can act as Lewis acids. Okay, so and Lewis bases are simple anions. Simple anions can act as Lewis bases. Examples are NO3 minus, Cl minus, OH minus ions. And molecules containing unshared pair of electrons, one or more unshared pair of electrons can act as Lewis bases. For example, NH3, it has one lone pair, and H2O, ROH. Those compounds can act as Lewis bases because those compounds have unshared pair of electron pairs, unshared electron pairs. And multiple bonded compounds. For example, CH2 double bond CH2, acetylene, this is called ethylene, this is called acetylene. Compounds, multiple bonded compounds can act as Lewis bases. Okay, so Lewis acids are compounds with in which central atom has incomplete incomplete octet, compounds in which central atom has vacant orbitals, and molecules having multiple covalent bonds as Lewis acids. And Lewis bases are simple anions and molecules having one or more unshared pair of electrons and multiple bonded compounds can act as Lewis bases, right? So these are the examples for Lewis acids and Lewis bases. From these three theories, we can conclude that all Bronstead acids are all Bronstead bases are Lewis bases, because Bronstead base is proton acceptor and Lewis base is electron pair donor. So if you observe OH minus ion is Bronstead base, and OH minus ion here is a Lewis base. So all Bronstead bases are Lewis bases, but Bronstead acids are not Lewis acids. Okay, this is very important because it should be borne in your mind that all BL bases are Lewis bases, all Bronstead-Lowry bases are Lewis bases, but Bronstead acids are not Lewis acids. Okay, so from these three theories, that is Arrhenius theory, Bronstead-Lowry concept and Lewis concept, with the help of these three concepts we can set that which is acid and which is base on the basis of different theories. HCl is a Arrhenius acid, acetic acid is a Arrhenius acid, CO2 is a, tell me, AlCl3, BF3, these two are Lewis acids, and of course CO2 and SO2, of course it has a limitation in the Arrhenius theory, but it acts as Lewis acids or non-aqueous acids. Okay, so these compounds or these acids can be called as non-aqueous acids. Okay, I shall explain the difference between aqueous acids and non-aqueous acids in the upcoming classes. Okay, that is the basis for several concepts, right? And this is the base according to Arrhenius, and this is the base according to Arrhenius, and these are the bases according to Lewis theory. So there is no theory, there is no appropriate theory to explain the acid base concept, and moreover there are two more concepts are there, that is Ushanovich concept or Sanovich concept. Sanovich concept of acid and bases, Ushanovich concept of acids, and or usually we call it as Sanovich concept of acids and bases. Okay, so Ushano acid is a chemical species which gives up cations, accepts anions or electrons. I repeat, Sanovich acid is a chemical species which gives up cations, accepts anions or electrons, and Sanovich base is a chemical species which gives up anions or electrons or combines with the cations. I repeat, Sanovich bases are chemical species which gives up anions or electrons or combines with the cations. simply we can say that all oxidizing agents are Sanovich acids, all reducing agents are Sanovich bases. Okay, it can let us take one example. Fe plus 2, Fe plus 2, Fe plus 3 system. Fe plus 2 gives rise to Fe plus 3 plus electron. Here you know very well that Fe plus 3 is a oxidizing agent. Fe plus 3 is a oxidizing agent. Oxidizing agent acts as a acid. And Fe plus 2, this is a reducing agent. This can act as a base, a cyano base. Okay. So, this is a Sanovich concept. Oxidizing agent, already I told you, oxidizing agent that will gain electrons. Here Fe plus 3 gain electrons, Fe plus 3 plus 1 electron, that gives Fe plus 2. So, this is oxidizing agent. So, according to this concept, Fe plus 3 is an acid. And Fe plus 2 is a reducing agent. Already I told you, reducing agent is reducing agent that will lose electrons. So, Fe plus 2 lost 1 electron, it forms Fe plus 3. So, it is a reducing agent. This acts as base. Next, another concept is Lux flood concept. Lux flood concept of acids and bases. Lux flood acid is oxide ion donor is base. 1 minute. Lux flood, before we are going to Lux flood concept, I come to Sanovich concept. Fe plus 2 is a reducing agent. Fe plus 3 is an oxidizing agent. We can apply this concept to all the oxidizing agents and reducing agents. And Lux flood concept. Lux flood concept is oxide ion donor. Oxide ion donor is a base. And oxide ion acceptor is acid. Okay. Examples are CaO plus SiO2, that gives CaSiO4, PbO plus SO3, PbSO4. Here you can see that calcium oxide, it donates oxide ion to SiO2 and it forms CaSiO4. So, it donates oxide ion. So, it is a base and it accepts oxide ion, it is an acid. And PbO, it donates oxide ion to SO3 and forms PbSO4. So, it is a base and it is a acid. SO3 is acid. Okay, so according to Lux flood concept, oxide ion donor is base and oxide ion acceptor is acid. And according to Sanovich concept, all simply we can remember that we can remind that all oxidizing agents are Sanovich acids, all reducing agents are Sanovich bases. Okay, so these are the theories which came forward to explain the acid base concept. From this theories, we can conclude that there is no appropriate theory to explain the acid bases. When we are explaining some compounds as acids or some compounds are strong acids, with respect to another theory, that acid may be a weak acid. And we can explain some compounds are acids on the basis of one theory, and we cannot explain that same compound on the basis of another theory. We cannot explain that compound as acid with the help of another theory. So, there is no appropriate theory for acid to explain the acid base concept. Okay. So, actually these are not asked in the examinations, but in the next class we shall discuss the strength of acids. Okay, it is very important concept which can which is usually often asked in the NEET and JEE examinations. Questions are being asked from strength of acids. Questions are not being asked from this concept. Okay, so thank you for watching.